Welcome to another great video. So in this video, right, what we'll be doing is we'll just be walking through the pre-June exam paper for physics paper 1. So this is just a walkthrough to show you how to answer most of the questions, right? So we took this one from Vhembe West. So yeah, but it should be good enough to prepare most of you grade 12 learners, right? So let us start. We will go in sequence, starting from question 1 until the last question. Okay, I won't read the instructions. You should know that instructions will always be there. So now here in question 1, we have a problem. A book rests on a table. Which one of the following forces will form an action-reaction pair with the weight of the book? All right, so remember, the action-reaction pair comes from Newton's third law. So when we say action-reaction pair, we mean if object A exerts a force, say this is my object A. If object A exerts a force, and then there's object B. In this case, we'll think of this as spheres, obviously. So I'll just make an example with electrostatics. Whenever you have two spheres, this is object A and object B. Actually, usually it's like this. If object A exerts a force on object B, right? It's just we'll have FA on B, for instance, on B, right, and then object B should exert the same force of equal magnitude on object A, but in the opposite direction. FB on A, let's call it like that. So object A exerts a force on object B, and object B in turn exerts the same amount of force but in the opposite direction on object A. So we're looking for a situation like that here. So this book will rest on a table, and then we are asked which one of these forces from A to D will form an action-reaction pair with the weight of the book. Okay, let's start here. So the weight of the book, remember, that is the Earth exerting a gravitational force on the book. So if we follow the very same principle, which is Newton's third law, it means the book must also apply a force on the Earth. So that force should be of the same type, right? So let's go through our list. Number A, force of the Earth on the book. It can't be number A because force of the Earth on the book is the weight of the book, right? So this one is ultimately out. Number B, force of the book on the Earth. Yes, so the force of the Earth on the book is our weight, right? So that's FA on B. And then now the book must exert the exact same amount of force back to the Earth, but in the opposite direction. So that can only be achieved by this one, number B. So our correct answer for here is number B. So we can continue and check for C. Force of the book on the table, that one won't work because that is a new action-reaction pair. That's a contact force now. Remember, the gravity force that the Earth exerts on the book, which is the weight, is not a contact force. So whenever you are looking for an action-reaction pair, the forces that are concerned there should be of the same type, and then additionally they should act on two different objects. So in this case, the objects are 1, Earth, 2, the book. So you have FA on B. Let's say this is my book and this is my Earth, right? So these are two different objects, but you have the same type of force between them. So this number C won't qualify because of that. it's a contact force, so it's ultimately out. It's a contact force and a gravitational force. Those two cannot be an action-reaction pair because they are different types of forces. Okay, now we go to number D, force of the table on the book. This is also a contact force. It won't work. In fact, this is what you would call your normal force. So yeah, C, D are out and also A is out, so our correct answer should be B. Let's use a red marker. Right, so that's how you would get number 1.1, or that's the logic you would use to answer question 1.1. So let's go to 1.2. You have a ball that is thrown vertically upwards, right? And then now we are being asked which one of the following physical quantities has a non-zero value at the instant the ball changes direction. Okay, so let's draw this situation, right? Remember, this is like vertical projectile, right? You throw a ball up, it reaches a maximum point and it comes back, right? So we are being asked at this point, which one of these physical quantities will be zero, right? Oh no, which one of the following physical quantities has a non-zero value at the instant the ball changes direction? Okay, yes. So it's non-zero, which means it's greater than 0. We start with A. Of course, before we go there, we know that at this maximum point, right, acceleration is 9.8 meters per square second, right? Because that's the gravitational acceleration, it's always there, right? And then we know that velocity at this point is 0 meters per second. We also know that the height, let's say this is where the ball started, right? So at that point I would have reached my maximum height, so that's H max, right? So those are the things we know about that point up there. Okay, so now let's go and check our variables that we've been given, or the parameters we've been given. I mean physical quantities, right? So A is momentum non-zero at that maximum point. Well, momentum is P, right, is equals to M times V. So we know that V is 0. So if I say 0 times whatever mass, I will get a momentum of 0. So it can't be momentum because we are looking for a non-zero quantity. Velocity, we just said velocity will be 0. It can't be velocity. And then acceleration, yes, is non-zero. Kinetic energy is calculated using half mv squared. We already know that velocity is 0. So anything multiplied by 0 is simply a 0. So kinetic energy won't work. And then that means acceleration is the one that's non-zero. It's 9.8 meters per square second, right? So that's the difference. I mean, that's the answer. All right, number 3, 1.3. So airbags in modern cars provide more safety during an accident, right? Okay, the statements below are made by a learner to explain how airbags can ensure better safety in a collision. Okay, so this learner makes these 3 statements. 1, the time of impact increases. 2, the impulse increases. Or 3, the impact force increases, right? So if you remember, for you to answer a question like this, you need the formula F net, or F is equals to delta P, which is change in momentum over delta T, right? So usually we relate our answers to this formula right here. Okay, so now let's get into it. Which of the statements above are correct? Okay, all right, so excuse me, which of these following statements are correct? Now if you remember, when you're using this formula, in this case, delta P will be the constant. Why are we saying it's constant? Because if an airbag is trying to stop you during a collision, because that's usually what it does, it comes out and then it stops you from hitting the dashboard, sort of, right? So your delta P will be definitely the same, because your VF and VI, it'll just be mainly VF minus VI, right? All of this obviously times your mass. Now we will keep delta P the same, right? So it's going to be same even if the airbag was not present, because the car will come to a halt anyway. So now what's changing is, what the airbag does is it increases the time to slow you down, over which you as a passenger will come to rest. So as it increases this time, what this does is it reduces the impact force, right? So it increases the time over which you come to rest as the passenger, and what that does in turn, it reduces the impact force, right? So that's what will normally happen. So now if we come and check here, we say the time of impact increases, yes. The impulse increases, no, because for you to increase the impulse, what's this? You would have to change the momentum, which we know the momentum will stay constant. Remember, impulse is equals to change in momentum, right? So you can't really rely on that. So now we know that momentum will stay constant, because your VF and your VI will be what's this? Your change in momentum will be constant throughout this whole situation, because you have a VF of 0. VF, I mean final velocity of 0. That is after the airbag or the car has stopped, right? And your VI, the speed at which you were initially traveling before the airbag deployed or before your car came to a halt, right? So definitely this one will be constant even if the airbag was not there, right? If we calculate your momentum before and after the collision, and then you take the change, that change is just, it's the same value. Now, so we can't say the impulse will increase. That one will not work. So what will happen is we cross this one out. Oh no, we said this one is fine. We cross this one out. Right, so the correct answer is this one. Now let's go to number 3 and check for it as well, because we are given that we can select 2 options here. The impact force increases. Yes. The impact force will increase, right? Because we are increasing, the impact force will decrease because we are increasing the time it takes to bring you as a passenger to rest. That's what the airbag does essentially, right? After the car crashes, what the airbag does, it slows you down, right? Because Newton's first law, you will continue moving. If the airbag didn't deploy, you were gonna probably go hit the dashboard or something. So it slows you down so that it can reduce the impact force. So we explain it using that formula right there. So now this means this one is correct. Therefore, our answer here is the one that will include 1 and 3. Statement 1 and 3. That is C. That's our answer. Okay. So this is how you would go about such a question. All right. So now let's go to this one. Okay. So here we are told that a stone of mass m is dropped from a height h above the ground. So ignore the effects of air friction. Okay. So if we ignore the effects of air friction, it means we can use the law of conservation of energy, for instance, right? So because we are ignoring the effects of air friction, so this is an isolated system. So now, which one of the following combinations in the table below correctly represents the kinetic energy and the total mechanical energy of the stone at the instant the stone has fallen through a distance of, okay, one fourth or a quarter of the height. Okay, let's see. Okay, so what I want us to do is we can think about it like this. So we have a stone, right? This stone is dropped from this height of h, and it drops, okay, it's at a height h, right? Now, so we are being asked what is the total kinetic energy and the total mechanical energy when the stone has fallen at least a quarter, not 0.25 of this height. So somewhere here, I think. Of course, you don't have to get it like 100% correct distance, but just know this is what the situation is representing, something like this. Okay, so now we know that mechanical energy, let's call this point A, let's call this point B, right? So at point A, let's start with mechanical energy at point A. The mechanical energy at point A, we can say it's E, let's call it EM, and you add the kinetic energy plus the potential energy, right? Kinetic energy is half mv squared plus mgh for the potential energy. Okay, so at this point we know that the velocity is 0 because they told us that the stone is being dropped. When something is being dropped, released from rest, and so on and so forth, those keywords in physics, they tell us that its initial velocity was 0. So it means our kinetic energy will be 0 there, plus then now our, let's call it mgha or something, the height at A. So at A, the height is at maximum, so we can leave it like that. So that means the kinetic energy at point A will just be mgh, right? I mean, the mechanical energy at point A will just be mgh. What about point B after it has covered 1/4 of the height? Right, you must be careful now. This thing has covered 1/4 of the height, right? Right. What that means is it's still left with some height here. So this is its new height. It's at a height of h minus that 1/4. So it's this new height is h minus 1/4 h. This should give you something like 3. Oh, let me use a different color. This one doesn't seem visible. This new height is h minus 1/4, which is 3/4h. Right, so that's our new height. That's the height we will use to calculate the potential energy at that point, at point B. Right, so we can go to our point B now and start finding at point B. Right, then our EM, mechanical energy, is still kinetic energy, but let me not rewrite the formula. It's kinetic energy plus potential energy, right? So that's half. We don't know what the kinetic energy is or the velocity. Let's call it EK, but we can substitute for the potential energy, mg. Our height now is 3/4h, right? So that's what's happening. We will have, so we have our potential energy. I took a stranger route to finding it, but it's fine. This is 3/4 mgh. Right, so our potential energy at point B will basically be 3/4 mgh. So let's go check in our table. Okay, we have 3/4 mgh, which is this one for our potential energy, right? We don't have any option with this 3/4 mgh. Let's see. Oh, that's potential energy. Let's see. We are required to find the kinetic energy and the total mechanical energy at point B. Okay, that's fine. It's not an issue. So we know the potential energy. Okay. Yeah, now we have this situation, okay? So at point B, we are trying to find what's the mechanical energy and what's the kinetic energy there. All right, let's work on it. So if you remember, the conservation of energy says if I take the mechanical energy at point A, it should be equals to the mechanical energy at point B, right? So what that means is I can take my mgh that we found. Remember this guy, mgh. Let's highlight it. It's this guy, right? That's my mechanical energy at A. And I equate it to my mechanical energy at B, that's EK, plus 3/4 mgh. So from this equation, you can see that I can solve for my kinetic energy, which is what the question wants, or it's one of the things that the question wants. So all of this is just that, right? I put it there. So now if you transpose and solve for kinetic energy, you'll find that our kinetic energy at B should be 3/4, 1 minus 3/4, it's 1/4 mgh, right? That's our kinetic energy at B. Okay, so now that we have that, we can then go ahead and find the mechanical energy at B. We can say EM is equals to 1/4 mgh plus 3/4 mgh. So now we are substituting this kinetic energy that we found into this formula here. So you'll just find mgh. That's it. So if you notice, you will see that I took the longer route, but what I should have done is I know that at point A, my mechanical energy is mgh. It means due to the conservation of energy, because friction is not present, at point B, I should have mgh as well. So I didn't have to calculate, but I did it so I can just show you guys how you would get there in an event where there were values involved and so on. But you don't always have to, right? If you can find it at one point, you know that at that point, if it's an isolated system, it should be equal to any other point after that. So at point B, at point C, at point D, you'll have the same mechanical energy. What will differ is the kinetic energy and the potential energy that make up that whole mechanical energy. Okay, so yes, that's your answer. So let's go check our options. We want where kinetic energy is 1/4. So our answer is D, basically. That's our answer, number D. All right, so yeah, these other ones won't work. The one that matches what we have is number, let's just make sure, EK is 1/4 mgh, right? And our, yeah, so number D is the one that makes sense. All right, so let's go to 1.5. The work done by a constant force F applied to an object to increase the object speed from V to 2V is W. Okay, now what is the work done by the same force to increase the speed of the object from 0 to V? Okay, it's not an issue. So now what we can use is Remember that the work or net work done is the same as kinetic energy. So work is the same as the change, not kinetic energy, sorry, the change in kinetic energy. So some people write it as E sub K, and then some they prefer to write it as KE. It's up to you and your textbook or what your teacher prefers, but I prefer E sub K to say kinetic energy, and then E sub P to represent potential energy. All right, so let's first check this one. When the object speed changes from V to 2V, what do we get? We get that our our work done so we know that it should be half m vf squared minus vi squared, right? I just factorized, but you can separate the formulas, it's not an issue. So this would be something like this: half m vf is 2v, so that would be 4v squared minus v squared. So this should give us 3/2 mv squared, right? So that's our original work done when the object speed changes from v to 2v, right? Now, what if the object speed changes from 0 to v? So what you would do is same thing, half m vf squared minus vi squared. So our initial velocity is 0, so we'll have v squared minus 0. So that's just half mv squared. Okay, so this is when the object speed changes from 0 to v, and then this is when the object speed changes from v to 2v. Let's call this 1, and then let's call this 2, just so that we can separate them. So you must obviously now understand, for me to get this, right, this is my original. So by what factor did the original change to become the new work done, right? So I noticed that if I were to take my new work done and multiply it by 3, I would get back the original work done, which is work 1, the one that the car or the constant force F achieves when it changes the object speed from V to 2V. Excuse me. So what that means is the work done by the force, constant force, when it changes the car speed from 0 to V is about 3 times less than the work done by the same constant force when it changes the object speed from V to 2V. So it means for me to get work 2, which is this one, I would have to go here and say 1/3 times work 1, which of course if I multiply this by 1/3, I'll just get 1/2 mv squared, right, which is exactly this. So that's how you look at it mathematically. Yeah, so alternatively you can just say work 1 divided by work 2, and then you get a ratio. Then you know that that ratio will represent the factor by which these two work done or networks differ, right? So it's a mathematical issue at this point, right? Not 100% physics. So again, I repeat, if I say work 2, I see that work 2 is 1/3 of work 1. right? So that's what I noticed here, because I calculated both of them, and then I'm comparing them now. So you can obviously take a ratio of the two, and you can say work 1 over work 2, and you would find that 1 over 2 mv squared over 3 over 2 mv squared. Okay, obviously those will go away, and then you'll find that work 1 over work 2 is 1 over 3. Then you can cross multiply, you'll get the same thing, which is A, right? That's another way of looking at it. So whenever you compare them, you can either look at them visually and see that, oh, okay, I see that if I were to multiply this, I would get this. Or if I were to multiply this one by 1 over 3, I would get the new one. Or you can divide. If you see that the maths for you, you have to take it step by step. That's still fine. Do what works for you. But at the end of the day, do what's right, and you'll get to the correct answer. Right, so that's how you would look at it. That's how you would look at this. Actually, questions like this is how you look at them. Okay, so let's go to (1.6). Which one of the following is not an application of the Doppler effect? Okay, let's check our options. Detecting the heartbeat of a fetus using ultrasound. Yes, that's correct. A blood flow meter. Yes, if you remember from your notes, blood flow meters, they use the same concept as the principle of Doppler effect to sort of show how fast your blood is traveling in your blood vessels, right? So it just shows how the speed of velocity or rate of flow of your blood through your blood vessels. So that one, yes, it's true. And then a light meter. No. So this one already, even the word light meter, it doesn't fit, right, the working principle of a Doppler effect, right? Because Doppler effects, we usually work with sounds, not light, and right. So now sound waves and so on. So now with a light meter, it usually measures the light intensity, right? So it does not really use Doppler shifts and so on. So for that reason, this one wouldn't really work. So this is basically something you would know off of your notes. So if you didn't read those long paragraphs in Doppler effect notes before the equations, you wouldn't know this. So it's important to read those ones. So since they said which one, I ultimately know that this has to be wrong, but this has to be right, sorry, but let's read it anyway. Measuring the speed of an approaching car using a radar. Yes, that's true. We've seen that even the speed cameras that you see on the road, they use this effect. They use the principle of the Doppler effect. Okay, so that's what happens. Okay, so let's go to 1.7 now. P, Q, and R are three charged spheres. When P and Q are brought near each other, they experience an attractive force. Okay, P and Q have to be unlike charges. When Q and R are brought near each other, they experience a repulsive force. So that means Q and R are like charges. Okay. Now, we are asked, okay, there was no specific question here, but this means you have to choose a correct description of what's happening here. So P and R have charges with the same sign. Okay, P and R have charges with opposite signs. PQ and R have charges with the same sign. PQ and R have equal charges. Okay, let's check it out. So assume, what I usually do is I test. I know that there can only be two charges, a positive and a negative. Let's say I choose P to be a negative charge, right? If P is negative, let's say this is my P, negatively charged sphere, and this Q. For Q and P to attract each other, it would mean Q is positive, okay? So let's carry over. Now let's go to this situation where there's Q and R now. There's Q is positive. For Q and R to repel, R would have to be positive. So, of course, they didn't tell me which one is positive or which one is negative, but I'm just using my logic to sort of check how it would work. So I know that for P, if P was negative, Q would have to be positive, because they have to attract each other, which is what the statement is telling me. They experience an attractive force. And since I'm assuming that Q is positive, and then I carry that to the situation where now I'm bringing Q and R closer to one another. So if Q is positive, for it to repel R, because that's what we are told, Q and R experience a repulsive force, it means R would also have to be positive. So when we check our options that were given now, P and R have charges with the same sign. Are they the same? No. So this one won't work. It's out. P and R have charges with opposite signs. Yes, I can take this one. On my scenario that I created, P is negative, R is positive. So yeah, I can say that's acceptable. And then P, Q, and R have charges with the same sign. This one won't work, because if P and Q have had the same sign, they wouldn't attract, they would repel. So this one won't work, right? And we are told in the statement that they attract, the first two, which is P and Q. So this statement is saying that P and Q are same sign. That wouldn't work, because if they were the same sign, they would repel instead of attracting, okay? So P, Q, and R have equal charges. We don't know. We are not told. Yeah, so it won't apply. There's no information to confirm the last one. So definitely B has to be the correct one. So obviously, even if you changed and said, let's assume P was positive, you'd get to the same conclusion. If P is positive, for it to experience an attractive force due to the presence of Q would have to be negative. If Q is negative, we put it here, obviously. For Q and R to repel, R would also be negative, right? So it means P and R have charges with opposite signs. So you still get charges with opposite signs at P and R, okay? So that's how you do it. That's how you think about it. Okay, so yes, that's the way you would answer this question. Okay, so let's go to 1.8. The magnitude of an electric field, a distance r from a point charge is E, okay? And then the magnitude of an electric field, a distance 2r from the same point charge, will be, okay, so this one, if you remember, we say E is kq over r squared, right? So we are not told anything about k or q. So what we can do is we just keep them, we do the same thing we did before. We can say E1, we found that E1 is simply E, which is kq over r squared, because our r is simply r, okay? Then E2, so this is just E, right? E2 is kq over 2r squared, and this will give us kq over 4r squared. Okay, so if you notice here, if we take out the 1 over 4 there, you'll have 1 over 4 times kq over, there's many ways of doing this, by the way, r squared. This is one of them. And the other one I showed you when we were finding the net work done using the change in kinetic energy. This is another way. So this is my E2, right? If you check, E2 is equals to 1 over 4 times KQ over R squared. And we can see that this KQ over R squared is the same as this. It's basically the formula for finding the magnitude of the electric field. So we can go here and say then, well, 1 over 4 times E, right? Because that's literally 1 over 4 times E. So our correct answer would be this one. So even if you did the other method I showed you before, where you take the ratio and you say E1 over E2, you would get the same thing, because you would get 1 over probably you would get 4 here. Let me see. Yeah, you'd have to say E2. Even if you say E1 over E2, you still need to make E2 the subject, right? This would be 1 over 4. Then you can say E2 is a quarter times E1, because you cross multiply, right? So you'd get the same thing. There are multiple ways of thinking about it. I'm just showing you another way, okay? So this is how you would do questions like these ones. So other people, what they do, you simply substitute ones for the things that were not mentioned. So but that's just another way of doing it. There's so many ways of doing these types of questions. Okay, so let's go to 1.9. A battery of EMF epsilon and a negligible internal resistance is connected in a circuit. Okay, now as shown below, the resistances of R1 and R2 are high. Okay, that's interesting. Okay, that's it. That's what we're told. And then now we have to choose the correct option. So if switch is open, what will happen? And then if switch is closed, what will happen? So we have this ammeter. Okay, so let's say the switch is open. Let's trace our current. Current will leave from the longer side of these lines representing a battery or cell. Then it goes like that, right? It won't be able to pass here because there's an open bridge there. The switch is open, so it can't pass there. So the current will come to this resistor R1, come all the way there, go to R2, and then so the ammeter will be measuring the current that had to pass through resistance R1 and resistor R2. That's what the ammeter will do. Okay, so this ammeter measures that resistor, not a resistor, sorry. It measures that current. It measures our total current when the switch is closed, open. So now let's look for an option like that. Ammeter reads only the current in R1. That's not true. We scrap that. Ammeter reads only the current in R2. That's not true. The ammeter reads the current in both R1 and R2. That's our answer right there. Oh, wait, but we still need to decide on the other column. So our answer lies between C and D, because C and D are saying the same thing. So let's go to when the switch is closed now, and let's erase this. When the switch is now closed, what will happen is here you will have this, right? The switch is closed now. So if you remember, current, let me put it in layman terms, current hates, it runs away from high resistance. So it will pick the path that has the least resistance possible. So what will happen is, if I close the switch, notice that I've done a parallel combination between the switch and the resistor R1. So when current gets here, it'll see a junction. Now it must choose, do I go to R1, do I split, and so on. So knowing that R1 has a high resistance, the current won't go there. It'll simply pass here in the wire. So R1 won't receive any current, unfortunately. This is a simple, or this is a classical example of short circuiting, where you short circuit something. You are like bypassing it by introducing a wire that has the lowest possible resistance compared to the resistor. Okay, and the current will definitely choose to flow to the wire instead of the resistor. So now it goes there. This means that the current that's being measured here is the current that will flow in resistor R2. So let's go look for that. Ammeter reads only current in R2. Okay, I can't choose A and B because, you know, I've already said those are incorrect. Ammeter reads the current in both R1 and R2. That's not true. So I know that C won't work. So D has to be my answer there. Ammeter reads only the current in R2. That's true. We take D. So that's how this question would be answered. Okay. All right. So let's go to 1.10. In the circuit diagram below, R1, R2, and R3 are identical resistors. Oh, okay. So what that means is if R1, for example, of course, was 5 ohms, since these resistors are identical, it means R2 would also be 5 ohms, and then R3 would also be 5 ohms. Right, so how do we represent a situation like this when we are not given the values? We would simply choose to say, well, it means that R1 is equals to R2 is equals to R3, and these are equal to a value called R. We don't know what R is. So instead of saying R is 5, which is not true because we are not told, we'll just say we'll represent it using the symbol R. So symbol R is our unknown resistance for R1, R2, and R3. Okay. So that's how it is. And now, okay, we know that the battery has negligible internal resistance, which means the voltage, if you were given that the voltage is 20 volts, for instance, it means this will be the supplied voltage to the circuit because there's no internal resistance to reduce this. Okay, if you remember. Okay, so the power dissipated by R1 is P. Okay. Which of the following is the power dissipated by R2? Alright. So how do we go about this one? So let's do what we normally do. Let's trace our current. Current will come this side. It passes there. That's total current, right? So R1 will receive the total current. Then you go there. There's a junction or a parallel combination. So the first branch will receive, let's call it I1. The second branch will receive, let's call it I2. Right. So because these are identical resistors, the current will split equally for these branches. So this total current will split in half. One half will go here. So this will be half I, right? And then this will also be half I. Okay. So we know that the power is often found using I squared times R, right? So for R1, this power would simply be I squared times R, because the current passing through R1 is that I, which is our total current. Okay. Now if we were to find now the power passing at resistor 2, let's call it P2, we would say now I squared times R, and then we'll substitute our current. Let's substitute our current. We know that our current is 1 over 2 times I, which is half the total current, times R. Okay, this will be 1 over 4 times I squared R. Now if you check, this thing is our power, is that, right? So that means our P2, which is the power at resistance 2, is a quarter, 1/4 of the power in resistor 1. So let's check which option satisfies this condition. Okay, it was A in this case. So we can say our answer is number A. So the rest, they won't work really. Okay, so that's how you handle questions like this one. So you just need to know your basics. You must know that, okay, if I have identical resistors, it means if current is splitting between them, current has to split equal, because the current splits according to the magnitude of the resistance in each resistor. Remember, we even use ratios sometimes to decide how the current will split across each resistor, right? And then, yeah, stuff like that, you must always remember them, because they will save you a great deal of time, like in a case like this. Okay, you could have used voltage, but that was gonna take you some time. That's another option that you had. For me, I use current because it was the easiest one to use in this case. Okay, all right, and then yes, let's continue to our question 2. All right, so question 2, we are told that 2 blocks of mass 5 kilograms and 3 kilograms respectively, we can see them here, the masses are labeled in the diagram as well. They are joined using an inelastic string of negligible mass. The string runs over a frictionless pulley. Okay, so we shouldn't worry about the friction in the pulley. The 5 kilogram block is on a horizontal surface, while the 3 kilogram block is on an inclined surface of 30 degrees with the horizontal. Okay, there's not much yet. Okay, the 5 kilogram block experiences a frictional force of 8 newtons. Okay, we are getting somewhere. So what I normally do, or what I advise learners to do, students, is you can go to your diagram and label some of these things. We know that there's a frictional force. See this direction here, it's telling us that these blocks are going this way. So if this block is going that way, it means that one has to be going also that way. Okay, that's the direction of motion of this system. It's going to, the whole system is basically going to the right. So the frictional force on the 5 kilogram block is pulling that side there. Let's call it our F, which is 8 newtons based on what we're told. It's kinetic friction, so we can call it Fk. Okay, and then the coefficient of kinetic friction between the 3 kilogram block and the surface of the inclined plane is 0.15. So we know that here there's also kinetic friction. We just don't know what it is yet. They only told us the coefficient. So the coefficient here, we are told that mu k is 0.15. Okay, so we have that. All right, so now what else are we told? The 3 kilogram block accelerates down the slope in the diagram below. Okay, we've already sort of deducted that from the diagram. Now let's draw our forces. We know that you'll have a normal force here. Let's call it N. Some people call it Fn like this. It's the same thing, it's up to you. Let's call it N, and then there will be a weight. I'll call it W. Some people call it Fg. That's still fine, it's up to you. Just do the right things. All right, so that's what we have. Now let's go to the 3 kilogram block. On the 3 kilogram block, we do the same. Remember, the normal force always acts perpendicular to the surface. So it will go like this. That's my normal force. The weight drops straight down from here. It'll just go down. Straight down from the block. Weight. So now remember, once you have the weights acting straight down like this in an incline, it means it will have components. So there will be a component going that way. We will call this our horizontal component. We will call it weight X. It's parallel to the surface, so that's why some people call it weight parallel. Okay, that's weight X. I call it weight X because it's in the X direction. And then there's another one that will go like this, perpendicular to the surface. That's why some people call it weight perpendicular. I call it weight Y. That's fine, the Y component of the weight and the X component of the weight. So where do we put our angle? We put our angle here, always, okay, between the perpendicular component and the weight vector. Okay, so then that's where we put our angle theta, which is 30 degrees. All right, so this is the situation that we have now. We are not done with our forces. We still have what we call tension from the string. So in this case, for the 5 kilogram block, the tension force is going that way. And then for the 3 kilogram block, our tension force will be going that way. Okay, so now we have all the forces that we need. Okay, so these are all the forces according to my interpretation and according to what the statement has told us. Right, so from here you can then now take out your free body. So for instance, if I wanted to take out the free body diagram for the 5 kilogram block, I would simply draw my dots. I would have my normal force, I'd have my weight, I'd have my tension. Okay, this tension is not in an incline. And I'll have my friction here. If you check, the tension and the friction vector are not the same length. The reason for that is because the block is moving that way, which means, well, whatever force is causing the block to move to the right is greater than the frictional force, which is opposing that motion. So that's why the length of the tension vector is longer than that of the frictional force vector. So then you have this one, the normal force and the weight, same length in this case. Right, so this is how you would sketch the free body diagram. Then I can also sketch the free body diagram for the 3 kilogram block if I wanted to, just from annotating my diagrams. I have my normal force pointing there. In I have, what else do I have? Oh, I have my tension T. Let's just write it as T. Let me make my dot bigger because I still need to add friction here. I have my frictional force Fk, and then I have my weight acting straight down W. So usually we don't include the resolved components, which is the Y component of the weight, which is Wy, and the X component of the weight, which is Wx. We usually don't include those in our free body, but we include them in our calculations. Okay, so that's one thing you must note. So yeah, let's continue and let's see if we can answer our questions now. All right, so our first question is, define in words the term kinetic frictional force. So if you use your exam guidelines or so on, usually these definitions are given to you, so all you have to do is just regurgitate them as they are. But obviously it's important to know what it means. For instance, when it comes to kinetic frictional force, we know that yes, friction opposes the motion of an object, but kinetic friction, it opposes the motion of a moving object, while static friction opposes the tendency instead. So it opposes that tendency of an object, of a stationary object, relative to a surface. So there's that distinction or that difference. So kinetic frictional force is for moving objects, and then static frictional force is usually for stationary or objects that are at rest, right? So it's the force that you experience before you start moving while trying to move whatever object. So you have to overcome that force first, and then your object will move. Okay, so how we would define it is basically it's the force that opposes the motion of a moving object relative to a surface. Okay, so yeah, this is the definition. Simply a force that opposes the motion of a moving object relative to a surface. So basically, when you say relative to a surface, it means there's a motion from both surfaces. So one of the surfaces is, there's the motion from both objects, which is the surface, and whatever object is on top of it. So the object would be a block sliding on a table, for instance. So there's that relative motion between these objects, which means the velocity of each is sort of different. One moves at a certain velocity and the other one moves at another velocity. So that's what that relative means, or that relative motion means in a way. So now let's go to 2.2. Draw a labeled free body diagram for the 3 kilogram block. Luckily for us, we've already done that. So I can just take this one that we already have here and bring it this side. That's 2.2 for you. So I can just put it here. Right, this is our free body diagram. So let me see if I can fix it. Must look nicer. Well, sort of nicer. That's Fk, frictional force, the kinetic frictional force. That's my normal force. Like I said, you can either make it N or Fn, it's up to you. So this is how the free body diagram would look like. So the number of forces here, 1, 2, 3, 4, will be equal to the number of marks that this thing is worth. Let's go check. So if you check, yes, it's equals to 4 marks. It means your free body diagram must have 4 forces. If you have 3, just know that there's one missing, because the mark allocation is clearly telling you that it must be 4. Okay, so that's how it works with free body diagrams. So we've already explained how we did that one. We can pass. Now we are asked to calculate the magnitude of the frictional force between the 3 kilogram block and the surface of the inclined plane. Okay, so what do we know? We know that frictional force is calculated using mu k times n, right? But do we know n? No, we don't know n. So our n here, if you remember, we say that n would have to be the weight perpendicular, which is the y component of the weight. So the y component of the weight, if we go to our triangle here, this triangle, we find that this y component is an adjacent sideways, so you have to use cos, right? Because if you take out the triangle, you'll get something like this. Let me draw it here extra. If you check my triangle, it's something like this. You have weight y, then you have weight x, and that's our 30 degrees there. That's the same triangle that we have here. That weight x that you see up there, it's the same side here. You can put it here. It's this part of the triangle. Okay, so if you remember correctly, that's what we do. And then now what we do as well is we know that for us to find weight y, we can say cos 30 degrees will be adjacent over the hypotenuse. So our weight y has to be this weight times cos 30 degrees when we cross multiply like this. This one goes there, that one goes there. So if you want to get more explanation as to the step-by-step of these components and so on, you can watch one of our videos where I was explaining how I think it's the grade 11 video where I was explaining how we do the cross multiplying, the components and so on, step by step. But here I'm assuming you already have these type of basics. Okay, so yes, that's how you would work it out. And then you can come now substitute here. We know that this is mg, that's our weight this, or before we get there, it's weight cos 30, which is mg cos 30 degrees. So usually I prefer substituting once whenever I can. I just substitute once and I get the final answer at the end. So what that means is I won't substitute yet here. I will take this equation and then come and substitute it for n. Okay, so that means my fk is mu k times mg cos 30 degrees. Then from here I can substitute everything and then get my final answer. 0.15 times my mass is 3 kilograms times my my gravitational acceleration times my angle, which is cos 30. Right, so then you would find your answer. Then I get 0.15 times 3 . So I get 3.82 what newtons. So if you leave out the units, just know that your answer is incomplete. Always include your units. Okay, so that was a simple 3 marks. So what you would have gotten was, there was a mark for this formula, a mark for this, no, there should be a mark for substitution I think, and then a mark for your final answer with units, right? But yeah, if you do everything here, I just broke it down step by step, but you don't have to include all of these steps. You could have started there and your following step was going to be this one, substitution, and then your final answer. Okay, so only 3 steps were required here. Let me see, 1 2 3 4. Okay, only 4 steps were required, which is 1 2 3 4, just these 4 steps. Okay, the other ones I was just breaking it down so that you see where it comes from, where the formula mg cos theta comes from. Okay, 2.3.2. The magnitude of the tension in the string. Let's see it. All right, so for this one, let's check. It is 5 marks. So here you have 2 options. It's either you use the option of, well, finding using the simultaneous equations, or you can, let's just do it. So if we check for the 3 kilogram block, let's come here, we have Wx. Well, we know what that is. We can calculate it during the calculation itself. And then we know Fk already. We don't know the acceleration. We are told that this block just accelerates down the slope. Let's check to make sure there was no constant. Okay, there's nowhere where it says constant velocity, because that was going to make our lives easy. Anyway, so what we can do is we can do that one. And then we have tension. Okay. All right, that's for our first block. So in our first block, the only unknown thing is tension. and acceleration. Okay, that's the 3 kilogram block. We don't know those two. So why am I concerned about the acceleration? Because remember, if we use Newton's second law, which is what this chapter is, this question is about, then say F net is equal to ma. If there's an unknown on the right side of the equation, the equal sign, you can't really solve for the unknown that is on the left hand side as well. So you'll have a simultaneous equation there. So you will only start noticing such things once you practice a lot. Okay, so obviously you don't have to notice it at first hand. So because remember, I would have said t, which is minus fk plus x, and then I'll get ma, right? So I know this fk, I know this wx, and then I know my mass, but I don't know my acceleration. So this would mean I have to sort of do a simultaneous equation. But let me see if I can avoid a simultaneous equation situation, because this is 5 marks. Okay, so I come to my other block. In my other block, if I say F net is equals to ma for my second block, which is 5 kilogram block, I would know my Fk, because I would have Fk, which is minus, plus my tension, and then I would have ma. Okay, so this side as well, I don't know my acceleration, I don't know my tension. Okay, so it seems like I have to use simultaneous equations, because then the common unknowns are tension and acceleration. Okay, so sometimes the reason I had to check is sometimes you might find that there was a known acceleration here, and then if you know the acceleration, you're simply going to transpose Fk and find t, right? But in this case, we don't know acceleration for both blocks. Okay, so let's continue. So we're gonna start with the 5 kilogram block. And we are using Newton's second law. We will say F net, the net force, is equals to the acceleration of the block times the mass. And then we are choosing right as positive. Okay, I'm indicating there that my right is positive. All right, so if right is positive, then Fk, which is my friction, which is opposing the direction of motion, will be negative, plus my tension is to the right, so it will be positive, is equals to my mass. Acceleration is also positive because it's going to the right. Okay, from here I'm told that this is 8 plus t, and I'm told that this is a 5 kilogram block. So what am I trying to solve for? I'm trying to solve for tension. So whenever you're trying to solve for something, you do not make that one the subject, especially since we'll be doing simultaneous equations here, unless you will be manipulating the equations. But what you can do, you can say A will be minus 8 plus t, or actually you can change this to look more friendlier. It's t minus 8, all this over 5, right? I just made A the subject, so you can call this our equation 1. Okay, some people would have done it here and called this equation 1. It's still the same thing. There are two approaches really once you get here to solving this thing. Okay, so I'll show you though. Let's start with the most common one, which is the one I'm using now. And then let's go to our 3 kilogram block. Okay, I need to add a page. Okay, we've added pages now. So we are from the 5 kilogram block. Let's check the 3 kilogram block. For the 3 kilogram block, what we can do is the same thing that we just did for the 5 kilogram block. We'll say the net force is ma. Right, let's go check the 3 kilogram block. We have Fk, T, and Wx in our direction of motion. Okay, all right, so minus Fk, I'm still choosing the same side as positive. We must stick to the same thing. minus T and then plus my parallel component of weight is equals to MA. So let me start substituting. Or before I do that, let me just do one last step. Minus T plus mg sine 30 degrees. Okay, now let me substitute everything. Fk, we found that it's 3.82, I think, at some point, minus T plus my mass is 3 times 9.8 sine 30 degrees. This looks like 300, but it's actually 30 degrees. Okay, much better. Is equals to 3A. Okay, so here we can also do the same thing. We can simplify this. Minus 3.82 plus 3 times 9.8 sine 30. Okay, I get that I will have 10.88 minus T is equals to 3A. So I can say 10.88 minus T over 3 is A. And I can call this my equation 2. So acceleration is the same for both equations. So I can say let equation 1 and equation 2 be equal. And then in equation 1, what did I find? T minus 8 over 5 is equals to equation 2. Then from here you can start solving. There is no one size fits all of solving once you get here, but there's a mathematically correct way of doing it. Okay, so it's up to you how you do it. There's no one way. Okay, it's all maths. Once you get to this point, it's all maths. Okay, so what I can do in my case, I can just cross multiply. I'll have 3T minus, but if you want me to take you step by step, it's fine. I'll have 3 times T minus 8. I'm cross multiplying now. What I did is I took this there and I'm taking this there as well. Okay, so, and then this is 5 times 10.88 minus T as well. Okay, so now I get 3T minus 8 times 3 is 24, is then equals to 5 times 10.88 is what, 54.4 minus 5T. Then you can group the T's. You'll have 8T this side, and then you can group the numbers as well. If I move this that side, it's 24 plus 54. This is 78.4, I think. Yes, 78.4 divided by 8. I get that my T is 9.8 newtons. So that's one way you would have done it. Okay, so yes, another way you could have taken these two equations. Let's take them here. From here, this was my equation 1, if you remember, equation 2. So I could have taken it from here, paste, right, and then I take my other equation from there. When you get, as soon as you get here, this one, copy. So this is maths. Once you have the equations for both, what follows after is just mathematics. Okay, so from here, what you could have done, you could have said, well, this is my equation. Doesn't matter which one is 1, which one is 2. It never matters anyway, right? What you can do now is you are trying to eliminate the A, because what you want is your T. So you can use that method in mathematics in simultaneous equations, where you simply find the common factor or the common multiple between 3A and 5a. So you're trying to make sure that when you subtract these two, you get a 0. So I know that if I multiply here by 5 and here by 5, I'll get 15, 15. But you're not only multiplying one side, you're multiplying the whole equation. So you'll have 54, was it 54.4 minus 5t is equals to 15a, right? And then you'll have minus 40. I think this will be plus 5t, right? A. Right, so if you check, now you can eliminate a by simply saying equation 1 minus equation 2. That would give you 54.4 minus 14 on the left hand side, right? On the right hand side, you will get 15a minus 15a. So if you solve, you'll notice that t will be something like 9 point, let's see, 90, I see 94.4 minus 10t. Yes, if you solve here, you'll get 99.44. right? So this is what you would get, 9.44 newtons. So the answers are slightly different, but mathematically there's nothing that you did wrong, okay? So that's another way in which you can solve a simultaneous equation. Okay, so yeah, but typically most people prefer the first way that I showed you, and then the other ones, it's a matter of preference after that. All right, so let's check number 2.4. How will the acceleration of the system compare if the positions of the 5 kilogram block and the 3 kilogram block are switched? So you take the 5 kilogram block and you put it there at the 3 kilogram, where the 3 kilogram block is. How will the acceleration be changed? All right. So the obvious answer here is it's going to be greater than. But why? Why is it greater than? It's because the driving force, if I can call it that, which is the Wx, right? That's the force that's causing this thing to slide downwards. It will be greater for the 5 kilogram block compared to the one for the 3 kilogram block. So let me show you what I mean. So if you remember, if you take the 5 kilogram block and you put it there, and we want to calculate the Wx for that, it would be 5, it's mg sine, right? Yes, mg sine theta. So that's 5. We're calculating Wx now for the 5 kilogram block if it was put where the 3 kilogram block is. It's mg, let's just write it here, sine 30 degrees. So if we put the 5 kilogram block where the 3 kilogram block is, you have 5 times 9.8 sine 30. This will give you, let's see, 5 times 9.8, that's 24.5 newtons. Okay, now what's the driving force when we had the 3 kilogram block? So this is 5 kg, this is 3 kgs. The Wx is, let's just substitute 3 times 9.8 times sine 30. Okay, 3 times 9.8 times 0.5, that's 14.7. Do you see that the force that's driving the system downwards has nearly doubled when we switch the blocks. So when it was the 3 kg block, the system was being driven by the parallel component of the weight of the 3 kilogram block, and the magnitude of that parallel component is 14.7 newtons. Okay, now we replace the 3 kilogram block and put the 5 kilogram block instead. So instead here we will put the 5 kilogram block, and the 3 kilogram block takes the position of the 5 kilogram block. Now the new driving force, or the new parallel component of the weight, will be from the 5 kg block, and that component is 24.5 kilograms. So it's way higher than initial, so we can be confident that it will be greater than. So that's our answer. Let me write it here. What is it? 2.4 greater than. That's what it is there. All right, so for this question we are done. Let's go to question 3 then. Let's see. Yes. So now what happened? Okay, this is question 3. All right, that's our question 3. A helicopter is moving vertically upwards at a constant speed of 8 meters per second. When the helicopter is at a height h meters above the ground, a stone is dropped from the helicopter. Okay, so let's see. We have this piece of information, right? So when the helicopter is at a height h meters, which is what we're seeing here, the stone is dropped from the helicopter. The stone reaches a maximum height of 150 meters above the ground. Okay, so the diagram below represents the motion of the stone from the instant it was dropped from the helicopter until it struck the ground. Ignore the effects of air resistance. Okay, before we even answer the question, this is what I always prefer. Annotate the diagram based on the information that you know. We are told that the helicopter is initially moving upwards at a constant speed of 8 meters per second. So what that means is, if I release the stone, right, because the stone is just dropped, it is not thrown, but it is dropped. Initially, before it moves down, the stone will initially travel at 8 meters per second up, and then it will run out of momentum, and then it will start falling down now. Okay, momentarily though, it will go up using that speed of 8 meters per second. Why is it doing that? It is due to Newton's first law. An object continues in its state of rest or constant speed unless it is acted upon by an unbalanced force. That's why even when you are seated in a car and the car suddenly brakes, you tend to move forward a little bit. That's because your body is trying to maintain that inertia, right? So that's the same reason that this stone, if you are dropping it, not throwing it, just dropping it, for a split second, of course I'm using layman terms now, but for a brief moment, it will just move up at that speed at which your vehicle is moving, which is the helicopter in this case, and then it will run out of that momentum, and then it will come back down, and then it will start going down from that moment onwards. Okay, so that's the first thing. It means here our V, let's call it V1, will be for the stone 8 meters per second. Okay, then the stone moves and reaches a maximum point where it now has to turn back. That's V2. Let's call this V2. We are naming it so that we can distinguish. Remember, in any vertical projectile motion, whenever we reach the maximum point, before turning, the velocity at that maximum point is 0 meters per second. Okay, and then all right, so now we continue. Goes down. So if I were to cut this thing here again, you would find that V3 here is the same as V1, which is 8 meters per second. So when the stone returns to where it started, it would have gained the equal an equal amount of speed as the initial one. Okay, so that's what happens, and then it continues further until it reaches the ground. At the ground, that's where the velocity will be maximum. All right, before it strikes the ground, that's our maximum velocity in this stone's journey. What else happens though? What happens as well is, as it's moving upwards, the acceleration due to gravity will be 9.8 meters per second. Right, so if we choose upwards as positive, the acceleration will be negative. So basically it is slowing down as it moves upwards. And then as soon as it comes this side, downwards, the acceleration and the direction of motion are the same. So yeah, but throughout the whole journey, the acceleration will be 9.8. Oh, no, my units are wrong. Meters per square second will be 9.8 meters per square second. That's our acceleration. So let's check. So if we choose up as positive in this case, our acceleration will be negative. If we are here and we are choosing up as positive, our acceleration will still be negative because acceleration is going down. So that's one thing to keep in mind. So acceleration is always acting down, which is the gravitational acceleration. So we use the gravitational acceleration because this is free fall. In free fall, we assume there's no other force acting on the object except the gravity. Okay, that's what happens. So I think we are done annotating our diagram based on the information that we are given in the question. Okay, so how do we know it's in free fall? Ignore the effects of a resistance. As soon as you see that, you know this is a free fall question, right? So this statement can come in multiple ways. The effects of a resistance are negligible and so on and so forth, or they can just simply tell you this is a free fall motion. It depends, right? There's multiple scenarios, but in this case we are told to just ignore the effects of a resistance or a friction, one of those. Yes, so now we can go to 3.1. Provide a reason why the stone is in free fall. I think they're supposed to say that day, after it was dropped from the helicopter. Simple, because there's no other force acting on the stone except the gravitational force. That's it. That's your reason, right? So let us write it down. For 3.1, simply put, right, we say, because you don't have to put that because, but if it makes you feel better, after the stone is released, the stone right? The gravitational force is the only force acting on it. The gravitational, it's as simple as this. The only force acting on it is the gravity. You can put it in another way, but it has to be along these lines, okay? Let's see, is the okay, the only acting on it. That's it. That's your 2 marks there. So after the stone is released, the gravitational force is the only force acting on it. That's why it's in free fall. After it was dropped from, let me use the same keyword they use, which is dropped, just to avoid issues. Okay, so now, what is the direction of the acceleration of the stone when the stone is at its maximum height? Okay, that's 3.2.1. The direction of acceleration of the stone. It's what I was explaining here. The gravity, the only acceleration acting on the stone is the gravity, and that gravity is always acting downwards. So the acceleration of the stone is downwards during its entire motion, by the way, because the only thing acting on it is gravity. So the answer here is simply downwards. That's it. Then 3.2.2, what are they saying now? Immediately after the stone is dropped from the helicopter, same thing, downwards. The only thing acting on this stone is gravity. This looks like downwards. Okay, so now it's downwards. Okay, so calculate 1, the maximum height reached by the stone above the point from which it was dropped. Okay, so they want us to find this height. When they say maximum height reached by the stone, it's this one, that h, from the moment it was dropped to the moment it reaches the highest point possible before it turns and goes back down. So let's just confirm. The maximum height reached by the stone above the point from which it was dropped. So you must be careful. Someone might be tempted to add that height with this one. So let's call this one maybe h max. I don't know. Yeah, so they don't want above the ground, but above the point at which it was, from which it was dropped. So that's very important there. Read ne? Don't just rush. All right, so the maximum height reached by the stone above the point which it was dropped, we have to first understand what we have. 3.3, what is it? We have the initial velocity. Our VI is 8 meters per second. We have the final velocity at the maximum height. Our VF is 0 meters per second. And of course, we have our acceleration. Since, let me choose up as positive, right? Then I can say this guy is 9.8. Right. So it's minus 9.8 because acceleration always acts downwards. So what we can do, if you chose down as positive, let's say you chose down as positive, it means your A would be positive. Okay, means your A would be positive. But then your VI would be negative. So I choose down as positive, as up as positive, because that's where the stone is going, so that the only thing I change is the acceleration. All right, so now let's calculate based on all these things that we have. If we go to our equations of motion, which equation of motion will allow us to find the height or the displacement that the stone covers in that in these given parameters? Let's see. We can find it if we check our formula sheet. This one won't work because it has time. We don't have time. Also, it doesn't have displacement or delta y or delta x. This one, yes, we have this, we have that, we have a. Okay, this one will work. Let's use this one. But since we are talking about vertical, we'll use delta y. X is maybe for horizontal, right? So we can use that one that says v f squared is equals to vi squared plus 2 times a times delta y. Delta y will be our height in this case. So we can say vf is our 0 squared, vi is our 8 meters squared, plus 2 times our acceleration is minus 9.8, and then our delta y is the maximum height, right? So you can leave it as delta y, you can call it h max, it's up to you. So now we know that we will get 0. This is 64, should be, yes, plus minus 19.6 here times h max. This is my h max. Therefore h max will be 64 divided by 19.6. You transpose and then you divide both sides by 19.6. I will skip that step for now, but you can do it step by step, and then you get 3.27 meters. Remember, if you leave your units, your answer is incomplete, and it's very much wrong. You can't exclude units. So that's how you would find the maximum height. This guy, that's one way that you would use to find. Usually that's the most common way or the easiest way to find that one. Okay, all right, now let's go to 3.3.2. What is the height h? So we can see that the total height from the ground to the maximum point that the ball reached before it dropped down is 150. So height h can simply be h will be the total height minus the one that we just calculated, which is h max, and this is 150 minus 3.27, should be 146 point something. 150 minus, it's about 146.73 meters. Okay, so that's our height h. Okay, that was relatively straightforward. Now we go to 3.4. Okay, 3.4, determine the time taken for the stone to reach the ground. Oh, nice. So what are they saying here? The stone starts here, it goes to maximum height. There's a time taken to reach maximum height. It then takes maximum height, it goes back down. There's a time taken there. So what we have here is something like this. Oh, this looks funny. I don't like it. Oh, much better. Right? That's our maximum point where V2 is 0. So the stone takes a certain amount of time to cover this path, right? It takes another time to cover that. So usually the time it takes for it to go from initial position to maximum is the same time it will take. Let me label this thing actually. Let's call this point A, point B, point C, and lastly the ground will be our point D. So what we're saying is the time taken to go from A to B will be the same as the time taken to go from B to C. You must remember this. Right, so if you calculate how long it takes from A to B, you will simply multiply by 2 to get the time taken from A to C. So that's 2 TAB or 2 TBC. Okay, something like this. Right, oh, I forgot the delta there. We usually say delta T. But you get the point. Let's do this. So this is what usually happens. Then CD is on its own, right? So usually you can use one of these, or you can find the time it takes from A to B and then find the time it takes from B to D. Or you find the time it takes from A to B and then you find the time it takes from C to D, right? So after finding A to B, you can multiply it by 2 to find how much time it took from A to C, and then you are only left with this portion of the trip. Then you can use another formula to find the time there. So let's see what we can do here. I'm just breaking down and reminding you of the basics. Okay, so the time taken for the stone to reach the ground Alright, so let me first add these formulas so I can show you which one we select for this case. So these are the formulas that you will also have in your formula sheet, if you remember when I showed you earlier when we picked our first one. So what we can do here, I think let's do this. We can first find the time it takes from A to B, and then from there we can find the time it takes from B to D, and then we add those together. That's the total time for our trip. So A to B and then B to D. Okay, do you see our annotated diagram there? All right, so let's say obviously whoever our examiner is doesn't know that we have A, B, C, D's. This is something we do in our separate piece, our working sheet. So we can say time to max height, right? So we're just telling them that now I'm calculating the time to the maximum height, and I say I know my initial velocity and final velocity. I know the acceleration, so I can use this equation to find the time to maximum height. Okay, all right, so that means Vf will be Vi plus A delta T. Alright, so Vf is 0, Vi is 8, plus minus 9.8 times delta T. Delta T to maximum height is 8 divided by 9.8. That is 0.82 seconds. So remember, this is A to B. So we just found the time from A to B. So if we take that time and multiply it by 2, we will get the total time from A, B, and C. So the total time to move from A to C, like what I was showing you here. Right, we can do that. So we can say now, let's see, what else do we know here before we continue? Oh yes, remember what we said as well is once the ball returns to the same position, it will have the same velocity as it had initial. So when the ball moves from A to B, it reaches maximum height at B, right? At that maximum height, the velocity will be momentarily 0. Then the ball starts falling again. When it reaches C, the velocity at C will be the same as the velocity at A, which was 8 meters per second in this case. Okay, so we can use that to find how long it will take to move from to the ground. And we already know the height h is 147 something like that, or 146.73. yes. So we can use that to find our time. So you're not supposed to do this in an exam, which is what I'm about to do. I'm doing it so that we keep the answers in the same screen. Okay, I'm avoiding going to a new page. What I'm doing now is I'm dividing like this. Don't do that in an exam. It's not allowed. If you do this, you will cost yourself marks. Okay, it's not a good habit. So I'm doing it here so that we remain in the same screen. We don't go to a new page. Now I know that times 2 max height, yes, and then now I can say time from H to ground, from height H to ground. Don't know what the examiner would know what you mean, as long as you are as clear as possible. So I can find that time as well using my equation here. I saw a nice equation here that would allow us to do that, which is this guy, right? So let me highlight it. I'm highlighting the equations we've used so far, those two. So we already know delta y, we know vi, we can find the rest. Okay. All right, so from H to ground. So now if I go from H to ground, I will have Vi and then delta T. But if you notice that will give us a quadratic equation, and then you have to use a quadratic formula. I don't need that. So what I mean by that, you would have delta, let me use a pen. You already have delta Y, right? And then you'd have Vi, you'd have 8 delta T plus 0.5 times 9.8, right? Delta T squared. So you see now, also you'll have a number here, I think it's the 147. This is a quadratic equation. I don't want that. So what I will do is I will change the position at which I'm starting from. I will start from H max instead. H max is up there at the top, right? Up there at the top to the ground, so that I know that Vi at H max is 0, because that's the maximum point before it just turns. So I'll just use that, and I know that height there is 150, so I can use that. It's straightforward. Let me come and show you here. H max is this point here, the apex, this one, point B, and I know at point B my maximum height is 150, and I know the velocity there is 0. Okay, you could have used the other one, but you were going to be starting at C going down point C, but it was going to give you a quadratic equation, and I'm avoiding that for now. So you would have gotten the same answer, but you will get 2 answers. Now you have to judge which one is the right one, which is still fine. If you can do that, do that. Okay. but because I am lazy, I will prefer for the simplest route possible. Now my delta y, that's the displacement. Remember, displacement is a vector, it has a direction. So since I chose up as positive, my displacement now, if I'm moving from point B to point ground, which is C, oh sorry, it's point D, from point B to point D, the displacement is in the downside, so I'll have a negative value here. So I'll make my 150 negative. Why? Because my displacement is in the downwards direction, and I chose upwards as positive. That's why my displacement is negative. It's a vector, remember. So then VI, I'll make it a 0 because I'm starting at the point, top point. This will just be 0. Let's make this 0 because 0 times anything is just 0. Then times 1 over 2. Since I am choosing up as positive, this will remain as minus 9.8. So I chose up as positive once, but for my entire calculations, I must not change that direction. Otherwise, I will get inconsistent results, okay? So you must be very careful there. Then delta t squared, okay? From here on, I know that my delta t, I will take a shortcut here, but it's the reason I'm taking a shortcut, it has nothing to do with physics after this point. It's maths, okay? So you must know how to do these. So you can just do that in your calculator. I know that I will get 150. The negatives will cancel each other, obviously, when I divide both sides. Divided by, what's 9.8 divided by 2? 4.9. And then I square this thing, because this side, I had something like this, right? So my delta t will be that square root of 150 over 4.9. That's 5.53. This is the time it takes to move from B to D. Now let's find the total time, because that's what the question wants, right? For the stone to reach the ground, yes. So the total time, let me move things slightly up. So that I can include my total time. Oops. Okay, I can move it here. All right, so total time, I can therefore say total time will be the time from A to B, which is 0.82, plus the time from B to the ground, from B to D, which is 5.53. Oh, I forgot my units there. And this will give you 6.35 seconds. So that's how long it takes for the ball to reach the ground. Okay, that's your time right there. Okay, yeah, that's what you would do to find that. Now, what else do we... So yes, just to illustrate my point, you see this time, this is the time to max height, right? It means if the ball takes 0.82 seconds to get to this maximum point here, which is what we got there, it takes another 0.82 seconds to get to point C. So by point C, the time would be 0.82 times 2. Should be 0. Oh yeah. So B, so del T C will be 1.64 seconds. And then at D, which is what we just found, is now the time at D is 6.35 seconds. So why am I marking these points? So the time here is 0, 0.82, 1.64. The reason I'm marking these points is because those are the points of interest. And when I draw my graph, which is the next question that I saw there, I must indicate all those points, okay? So let me show you. So the next question is saying, on the same set of axes, draw a velocity versus time graph for the stone and the helicopter from the instant the stone was dropped until it struck the ground. Okay, clearly show the initial velocity excuse me, clearly show the initial velocity for both the stone and the helicopter. Right, and then the time taken for the stone to reach the ground, which is the 6.35 seconds we just calculated. Okay, so they want us to show the helicopter, the initial velocity of the helicopter, and so usually you would start by saying velocity. You must title your graph versus time graph. We know it's a graph, so you don't really need to say graph at the end, but most people prefer saying that, so I'll just put it there. So yes, and then all right, so we have those in our arrows there. Usually you write your velocity this side, v in meters per second, and then here you write your delta t in seconds. All right, so for the helicopter and the stone, they both start at 8 meters per second. So we're going to put 8 here. Since we chose up as positive, it's fine. The 8 will be on the positive side of the y-axis, which our y-axis is the velocity axis. And then what will happen is the helicopter will continue at this speed because it's moving at a constant speed, remember. So let's say the dotted line represents the helicopter. This is my helicopter, right? This is how it looks like. And then the ball on the other hand will continue going upwards until it reaches a maximum height where the velocity is 0. This is where my curve intersects. Sure, let me change the color so that you can see it. Or should I use this one? Okay. The curve intercepts the x-axis, which is the time, and then it comes back down again until it reaches the ground at some point. Okay, so we are interested in that point. We are also interested in that point. So since they didn't ask us about the final velocity, we won't label it. We also don't know it, right? So we can start labeling now. Let me use red so that we can see the values. So there's 0 here. The time when it reaches maximum is 0.82. When it reaches the ground is 6.35. If they had asked us to show the time when it reaches the same point where it started, we're going to indicate it somewhere here and say 1.64. Okay, but we're not asked that, so we won't include it there. You don't include stuff that you were not asked. Otherwise it's like you are showing off. You don't want to be a show off, right? Right, so 6.35. Then what else were we asked? So the curve for the helicopter, just draw a solid line. Don't draw a dotted line. It's not good. So that's the helicopter, and then this is the ball. Okay, the helicopter continues indefinitely at constant velocity. We don't know when it stops. Let me see. Let's see the statement. Okay, yeah, they don't tell us if the helicopter stops or not, so it's fine. We'll just draw a straight line like that. That's for the helicopter now. Okay. All right, so yes, this is how you would answer question 3 of this paper. I hope you understood everything, and you are more than welcome to pause the video or reach out if you need help or more explanations, right? Okay, so this is where we will conclude the first part of this. Then we will continue again on another video for the remaining questions, which is question 4, 5, 6, 7, and 8. I think 4, 5, 6, 7, and 8. Okay. Oh, sorry. We still need to do question 4. So we will resume. Excuse me. We will end the video after question 4, and then we will continue with 5, 6, 7, and 8 on our next video. Okay. So let's just continue to question 4. All right. So question 4. A bullet of mass m traveling horizontally at 400 meters per second, we are also given that in the in the diagram, strikes a stationary 2 kilogram wooden block and becomes embedded in it. So the bullet and block together travel at a velocity of 4 meters per second. Okay, so we have a before and after. If you check, you can even label it if you want. This is before. In fact, let's use the terms that we used to. This is initially, the initial state. This is the final state. Okay, we can do that. And then, yeah, as illustrated below, ignore the effects of a resistance. So this is an isolated system. Okay, well, sort of. Excuse me. So this problem statement is fairly short. And then now we are asked to state in words the term impulse as used in physics. So impulse is usually just the product of the net force acting on an object and the time that force acts on that object, if I can put it like that. So that's your definition. So these type of definitions, some teachers, they would usually give you an exam guideline where there's a list of definitions that the recommended definitions, of course, because you cannot come up with your own definitions. You have to use the ones that are prescribed. So we usually define impulse as that. It's just the product of the resultant force acting on an object and then the time that net force acts on the object. So that's impulse. Yes. So yes, that's the definition. The product of the net force acting on an object and the time the net force acts on the object. So usually you would have something like this: F net is equals to delta P, if you've seen this formula, over delta T, right? So we are saying impulse is basically F net times this delta T, which is equals to impulse, right? So that's what this definition is saying: the product of the net force and the time taken. All right, and the time for which the net force acts on that object. All right, so that's what we're saying. So when they say in words, they mean you can't use a formula, because if they didn't specify whether you should define it in words or in formula, you can always pick the easiest way out, which is just writing out a formula and continuing with your life. Right, so usually they would specify whether they want it in words. They would never say in formula form. They barely say that. If you do find a question that says that, you are very lucky, especially in an exam. All right. Calculate the mass of the bullet. So since this is an isolated system, you can use the conservation of linear momentum, right, to find the mass of this bullet. So what we normally say is the momentum, the initial momentum, sum of the initial momentum is equals to sum of the final momentum, right? So that's what we usually say. And then what happens is, in the initial momentum, we sum the initial momentum of both objects. So there was the momentum of object 1, or let's call the bullet object 1, actually M1 V1. Let's call this M2 V2. No, sorry, V1. It shouldn't be V1, it's V2. Right? Mass 1, mass 2, velocity 1, velocity 2. Okay? So you can even use letters or use words. Some people write like this: the mass of the bullet. I don't prefer that. Or they would write mass bullet times velocity bullet. That's a long thing. So I'd rather just say M1 V1, which is, I know, 1. All my 1s are for the bullets. All my 2s are for the block. Plus M2 V2 initial, right, is simply equals to the sum again, but now in the final state, the sum of the individual momenta of these two objects. Okay, so now what I can do, I was told that the mass is, the bullet is currently, or was initially traveling at 400 meters per second, okay? And then it strikes a stationary block. So if this block is stationary, it means V2. So we can say V1 is equals to 400 meters per second. M1 is unknown, we call it M. They told us it's mass M. We come this side, we say M2, which is the mass of the block. We are told that it's 2 kilograms. And it is initially stationary. So V2 for the initial state is 0 meters per second. So when I say initial states, I'm saying before impact is my initial state. After impact is my final state. So before impact, what I mean by that is before the bullets hit the block, that's my initial state. That's what the system was initially at. And then my final states, I am referring to after the bullet strikes the block and they keep moving together. Okay, so in my final state, my M1 is still M, my M2 is still 2 kilograms, right? My V1 is 4, my V2, because now they are moving together, they will share this velocity. So V1 and V2 will be the same. So the block and the bullets are moving at the same velocity. They even tell you here, the bullets and block together travel at a velocity of 4 meters per second as soon as the bullet strikes that block. Okay, so let's go check. So now we have the whole situation. Initially, I start substituting. M1 is just M, I don't know what it is. Its velocity is 400 though. M2 I have 2 times 0. That's 2 kilograms times 0. I'm just substituting now. Final. So with the final, you know that the velocity is the same for both, but let's just do it. M1 is still M, we don't know what it is. M2, oh, they're traveling at this one. M2 is 2, and then they are both traveling at 4. So if you see V1 and V2, right, they are equal, as we stated here. V1 and V2 are equal because they are now moving together. It's like you when you are inside a car. You can't say you are moving at a speed that's different from the car. That's impossible. Then how are you staying inside the car? Right? The only time you will move at a speed that's different from your car is if you hit a tree and you fly out the window, right? But let's hope that never happens, okay? So now this is 400 m is equals to 4m plus 8. So direction is also important here. So since everything is moving in one direction, there's no need for me to use signs. But if maybe on the final state the block started moving to the left, my velocity would have been negative, assuming I choose right as positive. It's always important, right? But since everything is moving to the same direction, I don't have to change any signs or so on, okay? So now I can transpose that 4m. I'll get 396m. Imagine having 396m in your bank. Very nice stuff. So now you can divide both sides. 8 divided by 396, you get a mass of 0.02 kilograms. That's the mass of the bullet. So this is what? This is equivalent to, let's see, 20 grams. It's more or less reasonable for a bullet at least, right? So yes, now let us continue to 4.2.2. Okay, magnitude of the impulse on bullets during the collision. Remember what we said? We said impulse is simply F net times delta t, which is, it's basically the change in momentum. That's our impulse. So we don't know this side, right? But we know the change in momentum because we know the initial velocity of the bullet and the final velocity of the bullet. So what we can say is, therefore impulse, we know that impulse is equals to just change in momentum. So we can say m times vf minus vi. Okay, some people prefer writing it out like this: mvf, initial momentum. Okay, let me write it step by step. Final, initial. Okay, the initial momentum minus final momentum, which is mvf minus mvi. Why am I not using m1, m2, m3, m4? Because I'm dealing with one object now, so there's no need for me to introduce subscripts like 1, 2, and 3 and so on. Okay, so that one object I'm dealing with is the bullet. I'm concerned with the impulse of the bullet. So let's substitute. Oh, I can say that's where that v, this is where I factorized. Okay, so I'm just showing you where it came from. Mass is the same, it didn't change, so that's why you can factor it out. So we found that our mass is 0.02. Our what's this? Our final velocity is 0. Our initial velocity is 400. So you should get 0.02 minus 8 kilograms meters per second. Okay, so that is our impulse. Okay, so another unit for impulse obviously is Newton second, something like that. Newton second, because you're multiplying force and time. So if you want to use those, that's still fine. I just use the ones for momentum. So this, now you have to interpret what this means. If it's negative, it means the impulse is to the left, because we had chosen our right as positive. Opposite. Let me say opposite. They didn't tell us the direction. So that's what I can say when it comes to direction. Impulse is a vector. Impulse is a vector, so you must include direction. So our final answer is that one. So this answer also has direction, which is the minus sign. But if you want to interpret it, if you want to interpret the answer, and then that's what you would say. You would say opposite to the direction of motion. So the direction of motion was right according to our diagrams, but they didn't explicitly tell us that it's to the right. So I can't include direction that was not stipulated, that I was not told. So I'd rather say opposite to the direction of motion of the bullet. Okay. The bullet and the block travel on a rough horizontal surface. There's friction now. A distance of 2 meters before coming to a stop. Okay, that's interesting. Calculate the magnitude of the average frictional force between the block and the surface without using energy principles. Okay, so for this one, there are multiple ways of doing it as well. But since they said we can't use energy principles, so basically energy principles is your work net is equals to the change in kinetic energy, like this formula. Let me show you. You can't say, you can't use these type of formulae and so on. So we need to find this frictional force between the block and the surface. So first of all, we know that our total mass will be the mass of the bullet, M1 plus M2, right, which will be 2 plus 0.02, that is 2.02 kilograms. Okay, start there. Okay, so now once the bullet and the block are moving on a rough surface, the only force that will be acting there is the frictional force, the kinetic frictional force. So what we can do is we can say F net is equals to MA, right? We already know the mass of the system, which is this 2.02 kilograms. That's the mass of the block and the bullet. The F net is what we're trying to find, which is our FK. There's no other, we'll say minus FK because it's acting opposite to the direction of motion. The motion is that side, okay? Assuming we choose right as positive, or the original direction of motion of the system as positive. I always choose the original direction of motion of the system as positive. It makes life simpler. Unless, of course, it's convenient to choose something opposite to that, then that's a separate decision altogether. Okay, so now we are trying to find FK. We know M, but how can we find A? Because that would make our lives easier as well. We are told the distance that this thing will travel, and we already know the initial velocity, because come and check here. The bullets and block together travel on a rough distance of 2 meters before coming to a stop. Okay, so now we have a new situation. Check this. The block starts somewhere here. Right, the block and the bullets. Right? They just left after embedding on one another with 4 meters per second. So now this is my rough surface, this one. So it travels through this rough surface, and then at some point it stops. It can't go further anymore. And then this whole thing is 2 meters. Okay. So my VF, when it stops, will be 0 meters per second. What can I use this information for? Now, if you remember, there's a formula that says VF squared is VI squared plus 2A delta X. So all along, I've been trying to find my acceleration. Right. So I can use this equation of motion to find my acceleration, and then I can find the frictional force. So let's come and use it. 4.3. Let's go ahead and use it. We'll just use it on this side. We know that VF squared, VI squared, I think we used it earlier, but it was delta Y then. So check now. So we are told that it will travel for 2 meters before coming to a stop. So our final state is 0 squared. Our final velocity, sorry, will be 0. But initially, before it comes to a stop, it will be traveling at that 4 meters per second. Right? Where did we get the 4 meters per second? We got it from here. Remember, after the bullet strikes the block, they move together using a velocity of 4 meters per second. As soon as they move together at that velocity, they encounter a rough patch, which is a rough surface, right? And then they can only move for 2 meters in that surface before coming to a halt. So if you check our diagram here, that's exactly the situation I'm representing. Okay, so now we're trying to find what was that acceleration or that deceleration that caused the blocks to stop. Okay, we have 2 times A. We're already given delta X, which is 2 meters. From here, you can find A to be 16 over 4. Why is it minus? Because I'll transpose this that side. Okay, then I'll divide both sides by this product, 2 by 2. I skip some of the maths because I believe you are capable. So this is just 4. I know my answer makes sense that it's negative because remember the block is slowing down. It's not speeding up, it's slowing down. So it has to have a minus here. Okay, so now I can go ahead and find my frictional force. I can say F net is equals to MA. I am choosing that side as positive. So Fk will be negative. My mass is already 2.02. Acceleration is to the left, so it will remain negative. And then Fk, I multiply both sides by negative. I get 8.08, I think. 8.08 newtons. That's my frictional force. Okay, this is how you would answer a question like this one. All right, we have expended quite a lot of time on this paper. So for now, this concludes our part 1 of this pre-June exam paper. And yes, like I said, I hope you grasped most of the things I was showing you. If not, you can always reach out for help. All right, so catch you on our next video. And with that said, goodbye for now, at least.